Hello and welcome to this video tutorial for Creo Parametric version 3. The content of this tutorial is manufacturing within Creo. So Creo has the ability to produce toolpaths for NC machining processes such as milling. So currently I have a part within Creo. So this is the final part that I want to machine. So it's a simple block with a pocket and some holes. So we'll make an attempt at importing this into Creo Manufacturing and developing a toolpath. The main thing to note here is my coordinate system. So as you'll see later on, this coordinate system here will be better aligned to our milling operation. So our tool piece will rotate with respect to the Z axis and translate in the Y and Z axes. Okay, so if I go File, New, and I want a new manufacturing operation, and by default an NC assembly has been selected, so I can OK that. Okay, so I'll just turn my datum planes on. And you can see the menu layout and your work tree here is quite similar to what you would expect when making parts and assemblies. However, if we have a look through the manufacturing tab, we can see we can import the reference model. So that's similar to importing a piece if we want to make an assembly. So we can import our final part. We can then select our workpiece. So this becomes our stock. So this is the material that we're going to cut features away from. We can then define work centers and milling operations, such as face milling, drilling, or pocketing. So we'll start by opening our reference model. So we can import that. And similar to our assembly mode, if we're producing an assembly, we have this part floating in free space. I'm going to apply default constraints. That's snapped. That's fully constrained. Now I'll turn my datum planes off to keep the axes on. So the reason I set the axes in this way in our original Creo part was to facilitate importing. So typically your workpiece might be centered about this coordinate system in the top left-hand corner. Once we have our reference model, so this model forms our final produced part after our milling operations, we can then produce a workpiece. So this workpiece is also known as the stock, the blank material that we're going to cut away from. Now by default, because this is a rectangular piece, it's produced a bounding rectangle that encompasses our workpiece. Oops, might go back and edit that. However, we can set other options. So if we want to extend that workpiece, if we're using a bit of standard stock that has certain dimensions, we can apply those. So in our Z-axis, I'm actually going to add 2 millimeters, and that will allow me to demonstrate some face milling operations as we remove that top layer. And then I'll tick OK. So you can see the green overlay, which becomes our stock, and you can see the grey shadowing of our workpiece. And you can also see this in our work tree. Okay, we've got a reference model, we have a workpiece. It's now important to define a work center or a mill. So the most important selection here would be the number of axes. So whether it's a 3, 4, or 5 axis mill, we're just going to stick with 3. So translation in the XYZ direction. The other parameters we're going to leave as they are for the time being. For example, if we had an NC mill like in our workshop, and there was a certain tool set in the tool carousel, we could add those now. But we're not going to do that. We can add tools on the fly. So if we had a carousel, we could populate that, but we'll do that. We'll do that later. Okay, so we've defined a 3-axis mill. We can now define operations. So operations such as phase milling, end milling, pocketing, drilling, we can now define those as an operation step. So we'll click operation, and the first thing it's going to ask us for is a coordinate system. So we'll reference this, the top left-hand corner of our workpiece. And we can, by default, set a clearance plane. So we'll make that 10 millimeters. So this is the height that our tool pieces would retract to if they're moving about our workpiece. Obviously, in reality, this would be clamped or attached to our workbed, and you'd have to give due consideration for that so that our tool pieces don't impact with any clamping or restraining mechanisms. Okay, so a little bit of setup time in terms of importing our part, our workpiece, our mill, and our operation. But now we can start adding operations and removing material. So I'm going to start by face milling, so removing this 2 millimeter thickness of stock. I'm then going to look at pocketing this piece out using a roughing operation. And finally, I'm going to end that by a drilling operation, where I'll produce these 4 holes seen here. Okay, so we can go to the mill tab. And typically the workflow in this case is we set a mill window or a mill volume, so a volume that we want to remove our material from, and then we can insert milling or drilling operations based on that reference mill area. So I'll start with a simple face milling operation. I'll have to create a new mill window, and this is simply a silhouette. So we're going to select a plane. We'll select this top plane here. And the idea is we will face mill anything within that top plane up until our part that we want to keep. So that mill window becomes a reference in our work tree. And we can then add a facing operation. So reference, it's referenced our window, which is good. However, there's some data that we have to add. That includes the tool piece that we'll use. So we can add that. So previously we skipped this step, but we can now add tools. So we'll call this face mill 80 because it will have a diameter of 80 mil. Oops. You can also set shaft and spindle heights, but it doesn't particularly matter. For this case, we can apply that. So our tool ID1 becomes our face mill. But we need to add some more parameters. So this is what we refer to as our feeds and speeds. So the speed that our shaft spins for our cutting piece, and the rate at which the stock is fed into our tool. So we use 600 millimeters per minute is the standard units for feed. Our step depth, we'll call this 2 millimeters. Our step over, we'll make this 60 millimeters, so approximately 75% of the diameter of our tool piece. Other options, our clearance distance, we'll call that 20 millimeters above our workpiece, and our spindle speed will be 1800 RPM. It's also good practice to turn coolant on during our operation. And we can see that our toolpath is populated with this orange path, so our entry and exit points. We'll click OK. And now we can view that operation. So if we right click our face milling, we can then play our path, and we'll slow that down. And that's demonstrating our face milling operation. So it has a clearance here, a red clearance of 20 mil, and it has a step over of 60 mil. So there is some overlap between successive cuts, which is what we want to ensure all our material is removed. Okay, we can close that. We're then going to add another mill window that maps out this pocket, and we're going to remove that material. So we'll insert a mill window, and instead of a simple silhouette, we're going to sketch a profile. So we have to define a reference plane. So we're not going to define the top of our workpiece, but if we right click, we can define the top of our part. We can then sketch, and we can project this milling window here. So with the project tool, let's quickly trace over our pocket. So our operation is going to start at our selected plane and remove material that lies below this window here. We can complete that sketch. We can complete that. Okay, with this mill window selected, we can then undertake a roughing operation. So we're removing large pieces of material. By default, this window here has been selected. However, our only tool here is our face mill. So we can add an end mill. So we'll create new. We'll call this end mill 16 because it will have a diameter of 16 millimeters. We can then apply, and it's become populated in our tool carousel. Click OK. So our window is defined, our parameter, so our feed rate, step over, our feed rate should be 400 millimeters per minute, step over, say 10 mil. Our maximum step depth would be 7 mil. There's a wide range of tables for this that you can use to calculate our step depth and feeds and speeds. We'll have a clearance of 20 mil and a spindle speed of 3000 RPM. And we'll turn our coolant on. Okay. We can now right click. We can play that toolpath. We can increase that speed. And we can see the tool path that's been populated by default. If we were doing this in practice, we could spend a bit more time optimizing this toolpath and then including finishing processes. In our tool motions, processes, properties, there's a lot of other options that we can play around with, but we'll just leave this by default. So we could play around with those options to optimize cutting times, cutting speeds, etc. Okay, the final operation is going to be drilling out these holes. So they've been face milled, so now we can drill those out. So we want to start, we're going to use PEC drilling. As these holes are blind, it's impossible to drill these holes straight in one operation. In reality, the drill bit's going to have to drill down a few millimeters, remove that to release any swarf or cuttings, and it represents a pecking motion. So PEC drilling is often what it's called. We're going to have to add a drill bit. So this will be under drilling. This drill 10 millimeters. We'll set the diameter here. Apply that. Our references, now we need to select our hole axes. So we'll turn our axes on and control select. So our holes are populated. Under parameters, I can then enter some reasonably arbitrary speeds and feeds. So our PEC depth will be 4 millimeters, so it will drill 4 millimeters, release beyond our clearance plane, and then drill another 4 millimeters just to remove any swarf. Or 50 RPM. We'll put our coolant on. We can now view that operation by right-click, playing our path. And you can see the process of PEC drilling. So it's going to take several attempts to get to the bottom of this blind hole, but it's doing that to release any swarf or cutting, so we can speed that up. Okay, so it's been a very quick introduction to the NC machining platform within Creo. The basic workflow is to develop our part as a .prt file. We can then import that, select a workpiece. We can define a mill, so a 3-axis mill in this case, and we can then add milling operations. So a mill window which allows us to face, a mill window that removes this pocket, and then a final drilling step.